Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine you're standing outside on a perfectly clear night.
Oh, that sounds nice.
Right. You're far away from the city, no street lights, no light pollution at all. You were just staring up at a completely dark, quiet patch of the night sky.
Just you and the universe.
Exactly. The stars are fixed. Everything seems, peaceful, serene, ancient. But then suddenly, right in the middle of that black void, there's this brilliant, blindingly powerful double flash of energy.
Out of nowhere.
Out of nowhere. It lights up that patch of space with unimaginable violence. And then, almost as quickly as it appeared, it just vanishes. Complete silence again.
Here's the crazy part, though. If you were standing there relying entirely on your own human eyes, you wouldn't have seen a single thing.
Nothing at all.
Not a blip. The sky would have remained completely unchanged. Because, human vision is locked into this ridiculously narrow band of the electromagnetic spectrum. We just see visible light.
Right, the colors of the rainbow.
Yeah, exactly. But the universe, it doesn't limit its violence to the colors of the rainbow.
Which is terrifying, honestly, but fascinating at the same time. Because this flash absolutely happened. It was completely invisible to the naked eye, but it happened. And it left the smartest astronomers on Earth completely scratching their heads.
Oh, totally baffled.
We're talking about an event that occurred recently on March 5th, 2024. And to really figure out what happened out there in the dark, we've got to look at the initial alert logs, the multi-wavelength follow-up data from all over the planet, and, the theoretical astrophysics trying to piece this whole puzzle together.
It's a massive puzzle.
It really is. And it all starts with a highly sensitive piece of orbital technology called the Einstein probe.
The Einstein probe it's an incredible feat of engineering. It's a space telescope launched with a very specific and frankly very difficult mission.
Which of what?
Basically, to tirelessly stare into the cosmic abyss and just wait for something to explode. But, like we said, it doesn't look for visible light. It's equipped with these wide-field X-ray optics.
They call them lobster eye optics, right?
Yeah. It's super cool. It mimics the way a crustacean's eye can take in light from a massive field of view all at once. So it just scans the cosmos for these sudden, totally unpredictable, high-energy X-ray flashes.
And it has to be in space because our atmosphere actually protects us from X-rays. If the Einstein probe was sitting on, a mountain on Earth, it wouldn't see anything.
That is a crucial point. The Earth's atmosphere is incredibly thick. It acts like a lead shield against high-energy radiation, like X-rays and gamma rays.
Which is great for us.
Oh, yeah. If our atmosphere didn't absorb those wavelengths, life on Earth would be sterilized, period. So to observe the high-energy universe, we literally have to put our robotic eyes above the atmosphere.
Makes sense. So on this day in March, this orbital telescope is just doing its job, watching the dark, and it catches something entirely new.
A completely novel event.
Right. And it gets cataloged with the incredibly poetic name of EP240305A.
Ah, yes, the romance of astronomy.
I know, they love their naming conventions.
Yeah.
But essentially, that just stands for Einstein Probe, the year 2024, the month of March, the 5th day, and the first event of the day.
It's pure functional data management, but, the name isn't really the point.
No, the core mystery here is that this specific flash of X-rays completely defies existing classification. It doesn't fit into any known box.
Not a single one.
If we're playing cosmic detective, it's sort of like finding an animal in the woods that has the feathers of a bird, the scales of a fish, and the bark of a dog.
That's a great way to put it. The physical mechanics of what we're looking at just don't align with the categories we've spent centuries building.
And astrophysics relies on those categories.
Completely. The universe is usually quite good at fitting into our established models. We know the exact signature of a dying star. We know the signature of a supermassive black hole feeding on a cloud of gas.
So when something doesn't fit?
When a transient event entirely refuses to fit into those boxes, it forces a reckoning. It means our understanding of the fundamental mechanics of extreme stellar death is incomplete.
To understand why this event is forcing that reckoning, we need to look really, really closely at the precise timeline of the flash. Because it wasn't just a random burst of static.
No, it had a highly specific and frankly very weird heartbeat.
Right. The Einstein probe witnessed a brief X-ray flare, a massive spike of energy. And then this is the wild part. The energy dropped to nothing, dead quiet for about 200 seconds, and then boom, a second brief X-ray flare hit right after it.
In the realm of transient astronomy, which focuses entirely on things that change rapidly in the sky, a 200-second pause is deeply anomalous.
It feels anomalous just logically. I mean, when I picture a cosmic explosion, I picture a singular catastrophic release of energy. A star blows up. It expands outward.
A one-and-done kind of deal.
Exactly. A star doesn't blow up, pause for 3.5 minutes to catch its breath, and then blow up a second time. It makes me think of an engine stalling.
An engine stalling.
Yeah, like an old car engine that vapor locks. It sputters, goes completely silent while the fuel line clears, and then aggressively fires one last time. Does the universe actually build engines that can stall?
You know, that analogy of a stalling engine is actually incredibly close to the underlying physics we're talking about here.
Absolutely.
Oh, absolutely. If we look at standard cosmic explosions, like a supernova, that is a continuous outward expansion of energy and matter. It rises in brightness, it peaks, and it fades over weeks.
Right, a single structural failure.
But a double flare separated by a hard pause. That implies a central engine that is actively managing a flow of fuel.
So we aren't looking at a bomb going off, we're looking at a machine processing material.
Exactly. The machine in this context is almost certainly a black hole, or maybe a highly magnetized neutron star, and the fuel is an accretion disk.
An accretion disk. That's the swirling vortex of superheated gas spiraling down into the gravitational well. Right?
You got it. Black holes do not function like cosmic vacuum cleaners. They're more like a massive traffic jam.
A traffic jam.
Yeah, material is trying to fall in, but it's spinning so fast that centrifugal force fights against gravity.
So it literally has to wait its turn to cross the event horizon.
Yes. The gas rubs against itself, creating immense friction and heating up to millions of degrees, which, by the way, is what produces the X-rays.
Okay, so that's the flare. But where does the pause come in?
Well, accretion disks are highly unstable. They're governed by super complex magnetic fields. If those magnetic fields get tangled up, or if a massive clump of matter temporarily blocks the inner flow, the engine can effectively choke.
Wow.
The flow of fuel into the black hole stops. The X-ray emission shuts off, and that is your 200-second pause.
And then it clears.
Yep. The magnetic tension snaps, the blockage clears, a new clump of matter falls in, and the engine aggressively reignites, producing that second flare.
So a black hole basically choked on its dinner, had a 3-minute coughing fit, and then took a second bite.
That is a very visceral but very accurate way to describe it.
But here is the massive logistical problem with studying an event like this. You don't get a calendar invite.
Never.
We know years in advance exactly when a solar eclipse is going to happen, down to the millisecond. But a transient X-ray flash. By the time the Einstein probe's alarm bells start ringing down here on Earth, the event is completely over.
That is the fundamental hair-pulling frustration of transient astronomy. You are entirely at the mercy of the universe's unpredictability.
It's all reactive.
Completely reactive. These sudden flashes are the ultimate fleeting evidence. By the time the orbital telescope registers the photons, processes the data, and beams an alert down to ground control, the primary signal, the X-rays generated by that immediate violence, is already dissipating into the void.
Which means catching the initial flash is really only step one of the investigation. The actual science, the real detective work, happens in the frantic, highly coordinated scramble immediately after the flash.
Right. How do you study an explosion when the fire is already dying out?
Exactly. You have to mobilize every available observatory on Earth and in space as fast as humanly possible before the ashes blow away. And that introduces the necessity of what astronomers call a massive multi-wavelength follow-up campaign.
This is where the story turns into an international scavenger hunt.
Once the Einstein probe sounded the alarm on EP 24305A, researchers rapidly pointed multiple different telescopes, located all over the globe and in orbit, at those exact coordinates in the sky.
And they didn't just look for more X-rays. They gathered data across entirely different wavelengths of the electromagnetic spectrum. We're talking X-rays, infrared, optical, and radio.
This is critical for anyone trying to understand modern astronomy. We aren't just looking through glass lenses trying to magnify visible light anymore.
Not at all. The universe communicates across an entire spectrum. If you only look at the visible light, you're only reading one single paragraph of a massive encyclopedia.
For anyone listening who might not be a physicist, I want to make sure the concept of wavelengths really lands, because it is the absolute key to unraveling everything that follows.
It's the most important concept here.
Think of it like a car crash. If I'm standing on the sidewalk and I witness two cars collide, my eyes, which are basically biological optical sensors, see the dented metal, the shattered glass, the red paint of the car. That is optical data.
Right.
But if I pull out a thermal infrared camera, I don't see the red paint anymore. Instead, I see the intense glowing heat radiating off the engine blocks and the friction burning on the tires.
It's the exact same event, but a totally different set of physical data.
Exactly. So what about the extremes? What do X-rays and radio waves tell us?
If we push that analogy further into the extreme ends of the spectrum, the X-rays would represent the actual acoustic shock wave of the collision.
Like the loud crunch.
Yes, the violent, immediate sound of metal crushing. X-rays represent the highest energy, the most violent, immediate consequence of the event. They tell us about materials being superheated to millions of degrees in the immediate vicinity of a massive gravitational engine.
So X-rays equal immediate, extreme violence. The sound of the crash. So what do radio waves tell us? Because we always hear about radio telescopes.
Radio waves sit at the complete opposite end of the spectrum from X-rays. They are low energy with very long wavelengths. In your car crash analogy, the radio waves would be the long black skid marks left on the asphalt.
Oh, I like that.
Or maybe the sound of the police sirens echoing through the neighborhood hours later. They are the long-term aftermath.
But how does an explosion in a vacuum produce radio waves? There's no air for sound or anything.
It happens through a process called synchrotron radiation.
Synchrotron radiation.
Right. When a massive explosion happens, it rarely just puffs out in a perfect sphere. Often it blasts highly concentrated plumes of material relativistic jets out into space at nearly the speed of light.
Like a cosmic fire hose.
Exactly. As those jets slam into the interstellar gas and dust that was quietly floating around the star's neighborhood, it creates a massive shock wave. That shock wave operates like a cosmic particle accelerator.
So it's revving up whatever's already out there.
It catches electrons, traps them in magnetic fields, and whips them around at tremendous speeds. As those electrons spiral around the magnetic field lines, they bleed off energy in the form of a steady, glowing hum of radio emission.
Wow.
And because that shock wave takes a long time to plow through the surrounding gas, that radio hum can last for weeks, months, or even years after the initial X-ray flash has died out.
Okay, so armed with that understanding of the spectrum, let's look at the actual clues the astronomers gathered in the days following the double flash of our mystery event. Because the timeline of how these different wavelengths faded is bizarre.
Truly bizarre.
First, the X-rays. The data shows they vanished rapidly over a matter of days. That tracks with our engine analogy, right? The engine turned on, burned its fuel, and shut down permanently.
Exactly. A rapid X-ray decay points strongly to a highly energetic but very short-lived initial burst. The immediate violence was fast.
But then they looked at the radio emissions, and those lingered. They faded much, much more slowly, dragging on over several weeks.
Which is the definitive smoking gun for an evolving jet. That tells us that whatever exploded didn't just flash it, fired a concentrated beam of matter out into space, and we were watching the slow-motion aftermath of that beam plowing through the cosmic neighborhood.
The skid mark.
The skid marks, exactly.
Here is where it gets really interesting, though. The telescopes also spotted a faint, fading near-infrared source at the exact same location.
Yeah.
So there's some heat, some glowing embers left behind. But incredibly, and this is the part that makes this specific event so notorious, there was zero detection at optical wavelengths. Nothing.
No visible light whatsoever.
Which is astonishing. Usually when you have an event powerful enough to blast out high-energy X-rays and carve a massive radio-emitting jet through interstellar space, you expect a brilliant flash of visible light.
Oh, without a doubt. A standard supernova, for example, can outshine its entire host galaxy in optical light. To have an event this violently energetic be completely optically dark adds a profound layer of stealth to the phenomenon.
But how do you hide an explosion that big from regular telescopes? I imagine space is empty, but clearly something was blocking the view.
It forces us to analyze the environment where this explosion took place. Optical light is actually quite fragile compared to X-rays or radio waves.
Fragile.
Yeah, it gets easily blocked, scattered, and absorbed by cosmic dust. We call this process dust extinction.
Okay.
Think of trying to shine a standard flashlight through an incredibly thick, dense fog. The visible light just diffuses, scatters off the water droplets, and vanishes after a few feet.
But X-rays and radio waves don't care about the fog.
Exactly. An X-ray can punch right through that fog as if it isn't there. And radio waves being so long, just roll right over the far particles.
So the complete lack of optical light strongly suggests that this explosion happened in an incredibly dirty, dusty, chaotic region of space. The visible light was simply swallowed by the soot of its own environment before it ever reached Earth.
That's the only logical explanation for the missing optical data.
So, to summarize the crime scene for you listening, we have a physical engine that fired, stalled for 3 minutes, and fired again. It generated intense X-rays that died in a matter of days. It fired a jet that produced synchrotron radio waves for weeks. It left a tiny thermal signature of heat, and it was completely cloaked in dust, making it invisible to the naked eye. That is our exact set of physical clues.
That is the complete profile of our culprit.
Which means we are now ready for the ultimate game of cosmic elimination. To figure out what this new thing actually is, scientists couldn't just invent a new theory. They first had to meticulously prove what it isn't.
And astrophysics has a massive lineup of usual suspects to go through.
Let's walk through that exhausting list, because watching this single event systematically dismantle every single existing theory of stellar death is kind of thrilling.
Yeah.
Let's bring in suspects number 1 and 2, titled Disruption Events and X-ray Binaries.
All right, let's define the physics of those because they're some of the most violent events in the universe. A tidal disruption event, or TDE, happens when a star wanders just a little too close to a supermassive black hole.
Which is a bad day for the star.
A very bad day. Every black hole has something called a Roche limit. When a star crosses that invisible boundary, the gravity of the black hole becomes so intense that it pulls exponentially harder on the near side of the star than the far side.
Oh, I've heard this. The tidal forces just rip the structural integrity of the star to pieces.
Violently, it stretches the star out, shredding it into a long stream of superheated gas, a process cheerfully known by astrophysicists as spaghettification.
Spaghettification. It sounds fun until you realize it's a star being ripped into a noodle.
Right. And as that shredded star material wraps around the black hole and collides with itself, it circularizes into an accretion disk. It heats up immensely through viscous friction and releases massive amounts of X-rays. And it often launches a jet from its poles.
Okay, so a TDE fits the description perfectly. It's an X-ray transient with a jet. What about an X-ray binary?
An X-ray binary is essentially a localized stellar relationship gone very wrong.
A toxic relationship.
Oh, incredibly toxic.
Yeah.
You have a compact object like a stellar mass black hole or a highly dense neutron star orbiting very closely with a normal living star. The gravity of the compact object slowly siphons gas off its companion star.
It's just stealing its material.
Yep, it pulls the outer layers of the living star across the gravitational equilibrium point between them, building up that swirling accretion disk. Periodically, that disk reaches a thermal tipping point, becomes suddenly unstable, and dumps a massive amount of matter onto the compact object all at once.
Resulting in a flash.
A brilliant, violent outburst of X-rays.
So both of those suspects sound incredibly violent. Both produce X-rays. Both involve things being torn apart and eaten by black holes or neutron stars, which completely fits our engine theory. So why did the astronomers look at the data for EP24305A and completely throw them out?
It comes entirely down to the mechanical clock. The time scale of the physics is completely wrong.
Too slow.
Way too slow. When a supermassive black hole shreds a star in a tidal disruption event, it's a messy, prolonged process. The viscous time scale, basically the time it takes for that glowing, superheated disk of stellar spaghetti to actually drain into the black hole and cool down, takes months, sometimes even years. The X-ray emission drags on.
And our event's X-rays faded completely in a few days.
Exactly. The physics of a TDE do not allow an accretion disk of that size to drain and go dark in a matter of days. It was way too fast. And the exact same thermodynamic problem applies to standard X-ray binaries. Their accretion disk outbursts typically last for several months as the instability works its way through the disk.
But wait, I was reading about this, and there is a loophole, right? The astronomers did consider a very rare, short-lived subclass called fast X-ray transients. There are some X-ray binaries out there that can flare up and fade within a few weeks. Could this just be a really fast binary system?
It's an excellent point, and the researchers absolutely explored that loophole. But science relies on the totality of the physical evidence. While a fast X-ray binary might explain the relatively quick fade of the X-rays, They categorically fail to explain the other half of the spectrum.
Oh, the radio waves.
Exactly. Fast X-ray binaries simply do not produce the strong, lingering synchrotron radio emissions that were seen in this event. They do not have the sustained magnetic power to launch the kind of relativistic jet needed to plow through interstellar gas and create a weeks-long radio afterglow.
So you can't just pick and choose which data to believe. Because the radio jet exists, suspects 1 and 2 are physically impossible.
Spot on.
Okay, cross them off. Spaghettification is out. Let's move to suspect number 3. Thermonuclear bursts. Just the name alone sounds like a perfect fit for a blinding invisible explosion.
A thermonuclear burst is a truly mind-bending phenomenon. We're talking about literal nuclear explosions that occur on the actual solid surface of a neutron star.
For anyone who hasn't spent time thinking about neutron stars, we really need to pause and establish just how alien the physics of these objects are. Because if you don't grasp the density, you can't grasp the explosion.
That's true. A neutron star is the collapsed, dead core of a massive star that went supernova. They are incredibly small, usually only about 20 kilometers across. Maybe the size of a city like Manhattan.
Okay, city-sized.
But within that tiny city-sized sphere, they contain the mass of 1 or 2 entire suns.
So if you took a single teaspoon of neutron star material, how much would it weigh on Earth?
Roughly 1 billion tons.
1 billion tons in a teaspoon.
The density is incomprehensible. The gravity on the surface is so unimaginably strong that it completely overwhelms the electron degeneracy pressure that normally keeps atoms apart. It crushes the electrons into the protons, creating a solid sphere of neutrons.
Okay, so that's the surface. Where does the burst come from?
Well, if a neutron star happens to be pulling a slow, steady trickle of gas, mostly hydrogen and helium, off a companion star, that gas piles up on the neutron star's surface.
It just sits there.
It sits there and it gets crushed. Because the gravity is so intense, the pressure and temperature at the bottom of that pile of gas eventually becomes so extreme that it triggers what we call pick non-nuclear reactions. It triggers runaway nuclear fusion.
Like a massive hydrogen bomb covering the entire surface of a star.
Exactly. A hydrogen bomb the size of a city detonating all at once. It burns through the accumulated fuel in a matter of seconds to minutes, producing a massive sudden spike in thermal X-rays.
Okay, that sounds like a remarkably good fit. It's an engine, it's violent, it produces X-rays, it's sudden. Let me guess, the timing is wrong again.
Actually, the timing of a thermonuclear burst isn't a terrible fit for the initial flashes. The problem here lies in thermodynamics.
Thermodynamics.
It's like the heat. Right. Astronomers can analyze the specific spectrum of the X-ray light to determine the exact temperature of the emitting material, treating it as a black body radiator. While a thermonuclear burst is incredibly hot, the measured X-ray temperature of EP240305A was actually fundamentally too low to match the signature of runaway nuclear fusion on a neutron star surface.
Wait, it was too cold to be a nuclear bomb. I didn't see that coming.
It was the wrong kind of heat entirely. And beyond the temperature flaw, we run right back into the radio wave problem.
The skid marks strike again.
Always the skid marks. Thermonuclear bursts are surface events. They flash brilliantly across the crust of the star, but they do not launch massive, highly collimated, relativistic jets of material out into deep space from their poles.
So no jet, no radio waves.
Exactly. Therefore, the lingering synchrotron radio signal that lasted for weeks makes absolutely no physical sense in the context of a surface explosion. Suspect number 3 is ruled out.
The universe is incredibly picky. Okay. Suspects 4 and 5. We're running out of options in the catalog here. Magnetar giant flares and stellar flares. Let's tackle magnetars first.
Oh, magnetars. A magnetar is a highly specific, very rare type of neutron star where the internal physics have generated a magnetic field that is so absurdly powerful it breaks our standard models of physics.
How powerful are we talking?
We're talking magnetic fields 1,000 times stronger than a regular neutron star and trillions of times stronger than the Earth's magnetic field.
I read once that if a magnetar was located halfway between the Earth and the Moon, its magnetic field would be strong enough to wipe the magnetic strip data off of every single credit card on our planet.
That is entirely accurate. The magnetic fields are so stressed and twisted by the star's rapid rotation, a dynamo mechanism, that they exert immense physical pressure on the solid crust of the neutron star.
Because the magnetic field pushes against the solid crust.
Yes, and occasionally the actual crust fractures under the strain. This is literally called a starquake.
A starquake, that's amazing.
And when the crust snaps, the incredibly tense magnetic field lines violently snap and reconnect, releasing a catastrophic burst of energy in the form of alpha waves and high-energy radiation. This is a giant flare.
Okay, a snapping crust and reconnecting magnetic fields. That has to be it. That perfectly explains the mechanical start and stop, the double flash. The crust snaps, pauses, and snaps again. Why isn't it a magnetar?
It is purely a timing issue, but in the opposite direction this time. When a magnetar giant flare goes off, the release of energy is virtually instantaneous. They rise to peak brightness and then fade to almost nothing in a fraction of a single second.
A fraction of a second.
The physics of magnetic reconnection simply happen too fast.
But our initial flares lasted for several minutes, and there was a 200-second pause between them.
Exactly. 200 seconds is an absolute eternity for a magnetar. A magnetar giant flare operates on a timescale that is hundreds, if not thousands of times too fast to explain our transient.
So it's not a match.
It's like comparing the sharp, instantaneous crack of a whip to the slow, rolling rumble of an earthquake. They are fundamentally different physical mechanisms.
Okay, so magnetars are out. What about stellar flares? Like normal main sequence stars just throwing a tantrum. Our own sun has solar flares all the time that mess with our satellites, right? Could this just be a really, really big version of that happening on a distant star?
It's a very logical place to look. Stars are massive balls of churning plasma, and their magnetic fields get tangled and snap in the atmosphere all the time, releasing energy through magnetic reconnection.
Right.
And indeed, we see massive stellar flares from other active stars that produce significant X-ray spikes. But we run right back into the exact same physical wall we've hit with almost every other suspect.
The radio skid marks.
Yeah.
The jet.
Precisely. A stellar flare does not fire an artillery shell of matter into deep space at relativistic speeds. A flare is a surface eruption. It doesn't have the gravitational engine required to collimate matter into a jet that takes weeks to plow through interstellar gas. It completely rules out a simple stellar origin.
If you're listening to this and keeping track, watching this rigorous process unfold really highlights how methodical astrophysics is. It feels like a cosmic Goldilocks problem.
It's exactly what it is.
Every known violent event in the universe is either too hot, too cold, too fast, too slow, or completely lacking the physical mechanism to produce an aftermath jet. It is incredible how precisely scientists can read the thermodynamics and the decay curves and say, no, the physics simply do not allow for this.
It is a testament to how far observational astronomy has advanced. We aren't just looking at pretty pictures of the sky. We are reverse engineering the exact thermodynamic mechanics of the universe using nothing but a few photons of light captured by a telescope mirror.
So with all the usual suspects totally cleared from the room, with the tidal black hole shredding, the binary disks, the neutron star nuclear bombs, and the magnetic starquakes all tossed out the window, scientists were left staring at one remaining phenomenon.
The last one standing.
And this phenomenon checked almost all the physical boxes. Almost.
This brings us to the most devastatingly powerful explosions known to science since the Big Bang itself. We are talking about gamma-ray bursts, or GRBs.
Let's formally introduce the prime suspect. For a listener who might only know gamma rays as the fictional radiation that turned Bruce Banner into the Hulk, what exactly is a gamma-ray burst in a purely mechanical, cosmic sense?
A gamma-ray burst is the ultimate death scream of a massive star, or the catastrophic merger of two incredibly dense neutron stars. Let's focus on the massive star scenario, often called the collapsar model.
Collapsar model.
Okay. When a star that is dozens of times more massive than our sun finally runs out of nuclear fuel in its core, the outward pressure of nuclear fusion abruptly stops.
So gravity takes over.
Instantly. Suddenly, there is nothing holding up the crushing inward weight of the star's own outer layers. The core collapses in on itself in a fraction of a second, instantly forming a newborn black hole deep inside the star.
So the star is basically pregnant with a black hole that is about to eat it from the inside out.
That is a gruesome but accurate way to put it. As the rest of the star's massive envelope is collapsing inward, that newborn black hole begins to aggressively gorge on the infalling material.
Then it chokes.
Well, the gravitational and magnetic physics become so extreme that instead of swallowing everything cleanly, the black hole violently ejects a fraction of that infalling matter outward. It channels this material into two tightly focused, incredibly narrow jets that blast out from the north and south poles of the dying star at 99.99% the speed of light.
So the jet actually has to punch a hole straight through the collapsing body of its own star.
It acts like a cosmic drill. It drills right through the stellar envelope and erupts into open space. Within these relativistic jets, internal shock waves, where faster-moving material catches up and collides with slower-moving material, generate a blinding flash of high-energy radiation.
That is your gamma ray burst.
Exactly. They are so luminous that a single GRB lasting only a few seconds can briefly outshine the entire observable universe.
Outshine the entire observable universe.
Yeah.
That is a scale of violence that the human brain isn't really built to comprehend. So how did the physical properties of our weird little double flash line up with the theoretical models of these ultimate cosmic explosions?
They lined up eerily well, almost perfectly.
Let's look at the specific matching fingerprints. First, that strange 200-second pause, the stalling engine double flash we talked about earlier.
In the world of GRBs, that is actually a known, physically documented feature. It's literally referred to in the astrophysics literature as a double burst.
Wait, really? So the newborn black hole engine can stall?
Yes. The central engine, that newborn black hole feeding inside the collapsing star, can experience a severe hiccup. The accretion disk feeding it might become temporarily disrupted by chaotic magnetic fields or irregular densities in the infalling star matter.
So the food supply gets interrupted.
Right. This disruption can literally shut off the jet production for a few minutes, causing a dark pause. Then a fresh, massive clump of matter falls into the black hole, the accretion disk stabilizes, and it reignites the jet, causing a second burst. It is a rare phenomenon, but it is a known GRB behavior.
Okay, so the mechanical heartbeat perfectly matches a struggling black hole engine. What about the rest of the evidence? The X-rays fading in days.
A perfect match. The way the X-ray brightness spiked, peaked, and then dropped off incredibly rapidly perfectly mimics the typical decay curve or light curve of a gamma ray burst once the internal shocks of the initial explosion are over and the jet breaks free.
And the lingering radio waves, the skid marks that ruled out literally everything else on our list.
That is the most satisfying correlation of all. We talked about how those radio waves come from a jet plowing into interstellar space and accelerating electrons. Well, a gamma ray burst is defined by its ultra-fast, ultra-powerful jet.
Oh, I see where this is going.
As the external shock wave of that jet slams into the surrounding interstellar gas over weeks and months, it produces exactly the kind of slow-fading synchrotron radio afterglow that the Einstein probe follow-up telescopes observed.
Wow.
The double burst heartbeat, the X-ray light curve, the long-term radio afterglow, it all points beautifully, flawlessly to a GRB.
I can only imagine how deeply satisfying that moment in the scientific process must be for the researchers. You spend days ruling out everything else. You're staring at a massive mystery, and then finally you overlay the data on a gamma ray burst model, and you find an exact match in the physics. It has to feel like a massive victory.
It really does. It is the exact moment where chaotic data suddenly snaps into a beautiful, predictable order. Science relies heavily on pattern recognition and physical modeling. When you perfectly match the curve of the fading light, the exact timing of the engine decay, and the long-term presence of the radio shockwave, you feel like you finally have a solid grasp on the physical reality of what happened billions of light years away.
Well, I hate to be the one to interrupt the celebration. I really do. But as we synthesize all this data, there is one massive, glaring physical paradox with calling this event a gamma ray burst.
The defining characteristic itself.
Exactly. Where on Earth are the gamma rays?
Yeah.
Absolutely zero gamma rays were detected by any observatory during this entire event. None. Not a single photon of gamma radiation hit a detector.
Which forces astrophysicists into a very uncomfortable corner.
It honestly baffles me. How can you confidently publish a paper saying you found a gamma ray burst if there are no gamma rays? That is like me calling you up and saying I am standing in a torrential rainstorm, but confirming that not a single drop of water is actually hitting the ground.
It's a tough sell.
It completely defies the fundamental definition of the event. It makes zero logical sense.
It sounds exactly like a paradox, and it is. Because of this missing definitive proof, the scientific community has been forced to coin a highly specific and, frankly, somewhat contradictory classification for this exact type of event.
What does it call it?
They officially refer to it as a gamma-ray dark GRB-like event.
A gamma-ray dark GRB-like event. That is the scientific equivalent of shrugging your shoulders while using very big, very expensive words.
It is a profound admission of scientific caution. It acknowledges that while the mechanical behavior of the engine completely matches a GRB, the final high-energy output does not match our expectations.
So it's not a dead end.
No, this paradox is actually where the most fascinating, cutting-edge astrophysics begins. If the physical engine of a gamma-ray burst is running, if the core collapsed, if the black hole formed, if the jet launched, and if the subsequent X-rays and radio waves are ringing out into space but the primary gamma-ray signal is missing, that implies that something physical, something mechanical, is hiding the main event from us.
Okay, so the blast definitely happened, but the universe somehow put a blindfold on us. How does that happen physically? What are the mechanisms that explain where the gamma rays went?
Astrophysicists have proposed 3 main theoretical models to explain the missing gamma rays, and each one tells us something profound about the chaotic, messy environments where these massive stars die. Let's break them down mechanically. Theory number 1 is the off-axis jet.
Off-axis. Okay, so earlier you mentioned that a GRB isn't a spherical explosion that expands equally in all directions. It's a tightly focused beam, like a laser or a lighthouse firing from the poles.
Exactly. Because the material in that jet is moving at virtually the speed of light, extreme relativistic physics come into play. There is a phenomenon called relativistic beaming.
Relativistic beaming.
Because the jet is moving so fast, the Lorentz factor dictates that the vast majority of the light emitted by the particles in the jet gets heavily beamed forward, concentrated in a narrow cone pointing in exactly the direction the jet is traveling. If that incredibly narrow, highly concentrated beam happens to be pointing directly at Earth, we see a blindingly bright gamma ray burst.
But what if it's not pointing at us? Let's go back to an earthbound analogy. If someone points a high-powered, blinding tactical flashlight directly into your eyes in a dark room, all you see is intense, blinding white light. That's your direct, on-axis gamma ray burst. But if they turn that flashlight 90 degrees, pointing it to your left, you don't get blinded at all. You don't see the beam directly. You just see the ambient glow of the light scattering off the dust in the air.
That is precisely how an off-axis jet operates. If the relativistic jet of this collapsing star was pointing away from Earth, even just by a few degrees off our line of sight, the relativistic beaming effect means we would completely miss the narrow, blinding beam of high-energy gamma rays.
But the jet still exists.
It still exists. It still slams into the surrounding interstellar gas and creates an expanding external shockwave. As that shockwave slows down and expands laterally in all directions, it creates the ambient glow, the broader X-rays, and the slow-fading radio waves.
We completely missed the primary high-speed bullet, but we caught the expanding ripple in the air.
That's a perfect way to visualize it.
I love that. It feels like a very elegant solution. It doesn't require us to invent any weird new physics or rewrite the textbooks. It just requires a slightly bad viewing angle from Earth. So what is theory number 2?
Theory number 2 is significantly more violent and messy. It relies heavily on the physical structure of the dying star itself. It is called the choked jet model.
A choked jet. That paints a very vivid, suffocating picture.
Remember the internal sequence of events we discussed. The core collapses, the black hole forms in the center, and it tries to punch a relativistic jet of energy straight outward through the outer layers of the dying star.
Right, the cosmic drill.
But stars are not uniform. What if the progenitor star is a massive Wolf-Rayet star with an incredibly dense, thick outer envelope of gas? What if the physical density of the star is simply too much for the jet to penetrate?
The jet literally gets stuck inside the star.
Exactly. The explosion occurs, the massive release of gravitational energy happens deep inside the core, and the jet launches. But as it drills outward, it encounters too much resistance. The jet of energy simply fails to fully punch through and break out of the dense surrounding material of the stellar envelope.
It just stalls out.
It rams into the star's massive outer layers, dumps all of its incredible kinetic energy into that gas, and effectively smothers itself. The jet stalls, it chokes.
So it's like lighting a powerful firecracker inside a solid bowling ball. The explosion absolutely happens, the chemical energy is released, but it never breaches the surface. It just violently vibrates and heats up the ball from the inside.
That is a fantastic mechanical analogy.
Yeah.
Because the jet never breaks free into open space, the internal shocks that normally produce those high-energy relativistic gamma rays are never allowed to form in the open. The gamma rays are trapped and absorbed.
But the energy has to go somewhere, right?
Yes. The immense heat and pressure from that failed, choked jet still managed to superheat the outer layers of the star, creating a massive cocoon of energy. When that cocoon finally bulges and breaches the surface, it releases a massive, slower belch of thermal X-rays. And as the outer layers of the star slowly expand and eventually collide with interstellar gas, you still get a radio afterglow.
Wow. So an entire massive explosion happened, the black hole fired its ultimate weapon, and the star essentially swallowed it whole. The star contained its own destruction just long enough to hide the gamma rays.
It's a terrifying thought, but physically it works.
That is incredible. That brings us to theory number 3, which sounds like the absolute messiest option of all the theoretical models, the dirty fireball.
The dirty fireball theory is a fascinating variation where the jet does actually manage to break out of the star. It doesn't choke. It successfully punches through the envelope.
Okay, so it gets out.
But instead of being a clean, pure beam of highly accelerated plasma, the jet is overwhelmingly contaminated.
Contaminated by what? Space is a vacuum?
Contaminated by the dying star itself. This is a concept known in astrophysics as baryon loading. As the jet was violently drilling its way out from the core, it scraped against the sides of the star. It picked up too much extra cosmic material, too many heavy baryons, specifically protons and neutrons from the dying star's envelope.
Like a snowplow picking up too much snow.
Exactly. It got physically weighed down by the mass of its own host. It was loaded with too much dirt.
So the engine works perfectly, it broke free into space, but it was just hauling way too much physical garbage to run efficiently. Mass is the enemy of speed.
Precisely. To produce high-energy gamma rays, the particles within the jet need to be traveling incredibly close to the speed of light, highly relativistic speeds, so that when they collide in internal shock waves, they generate extreme high-energy photons.
But they can't because they're too heavy.
Right. If the jet is heavily burdened with all this heavy, dirty baryonic matter, the physics of momentum dictate that it simply cannot accelerate to those ultra-relativistic speeds. The extra mass acts like a massive anchor.
So what do we see?
The jet still blasts out into space. It still produces a massive external shock wave that generates the X-rays and the weeks of radio waves, but the excess dirt dampens the internal speed, effectively swallowing its own capacity to produce a clean gamma ray output. The cosmic fire is burning, but it's completely choked with heavy soot.
An off-axis jet missing us by a few degrees. A jet suffocating inside the dense envelope of its own star, or a dirty fireball weighed down by the heavy debris of its own creation. It is genuinely fascinating how these 3 highly mechanical theories completely reshape how we as humans think about space.
It really changes the perspective.
We are so used to seeing these beautiful, clean, sterile images from the James Webb or Hubble telescopes, the perfect mathematical spiral galaxies, the pristine glowing nebulas. But these theories tell us that on a mechanical, physical level, the universe is incredibly chaotic, messy, and fundamentally inefficient.
It's far from perfect.
Explosions don't happen in a sterile vacuum. They have to fight through thick gas, heavy dust, and the crushing gravity of their own environments.
It is an incredibly turbulent, almost violent environment. And realizing this is a paradigm shift for astrophysicists, we are beginning to understand that the clean, perfectly brilliant gamma ray bursts we've been observing and classifying for decades might actually be the extreme exception rather than the rule.
Oh, wow, really?
Yeah, they might just be the lucky ones. The rare events that manage to fire perfectly straight down the barrel without hitting any dense obstructions or scraping off too much baryonic dirt.
Which means there could be millions of dirty, choked, or off-axis explosions happening all the time that we just entirely miss because they don't produce the blinding gamma ray flash we traditionally look for.
Exactly. And that profound realization brings us back to the ultimate, somewhat conservative conclusion that the researchers had to arrive at when formally classifying the event.
Right, because without the definitive gamma rays, no matter how perfectly the X-ray curve or the radio skid marks match the models, they can't put a stamp of 100% certainty on it. The scientific method demands proof. So what is the final official classification they settled on in the literature?
Because they cannot firmly establish a pure GRB origin with the current multi-wavelength data, they simply can't prove definitively which of those 3 theories is the correct physical mechanism, or if it's something else entirely new that we haven't theorized yet. They classify it very broadly based only on the observable facts.
Which are?
They call it an extragalactic fast X-ray transient.
Extragalactic, meaning the physics confirm it happened far outside our own Milky Way galaxy, deep in the cosmos. Fast, because the engine stalled and faded in a matter of days. X-ray transient, because that high-energy burst was the primary physical signal we caught. It is a very literal, very cautious name.
It is the absolute essence of scientific caution. You state exactly what the physical data proves and absolutely nothing more. But the broader implications of this highly cautious classification are staggering.
How so?
It proves definitively that faint, quirky, heavily obscured events like this are incredibly easy to miss. If you think about the sheer volumetric scale of space out there, it is overwhelming. These subtle gamma-ray dark flashes, these choked and dirty explosions are constantly being drowned out and overshadowed by the brighter, more obvious, clean, cosmic explosions.
It's like trying to listen to someone whisper a complex secret to you while you are standing in the middle of a heavy metal concert. If you aren't paying exact, undivided, highly calibrated attention to that specific frequency, you are never ever going to hear it. The noise of the universe drowns it out.
And this is exactly where we have to focus on the absolutely vital role of observational technology in modern discovery. This entire physical mystery, this entire peeling back of the curtain on the messy, dirty universe is entirely reliant on the physical tools we build and launch into orbit.
Like the Einstein probe.
Yes. Without highly sensitive, specialized instruments like the Einstein probe, specifically waiting in the dark, staring unblinking through lobster eye optics, looking for these faint X-ray whispers, we would never have even known this event happened. It would have vanished into the void forever.
And even if the probe had seen the initial flash, if humanity hadn't built the infrastructure to instantly trigger a massive, immediate multi-wavelength follow-up from other optical and radio telescopes across the planet, we wouldn't have any of the physical clues.
We'd be blind.
We wouldn't know about the lingering synchrotron radio waves. We wouldn't know about the dust extinction blocking the optical light. We wouldn't be able to calculate the thermodynamics to rule out a neutron star explosion. We would just have a single, meaningless blip on a computer screen and zero context to understand it.
The synergy between space-based wide-field monitors and ground-based rapid-response telescopes is the only physical way to catch these fleeting, transient events. EP240305A proves beyond a shadow of a doubt that there is an entire vast spectrum of quiet violence happening in the universe. We're only just now finally building the mechanical eyes sensitive enough to see the hidden machinery of the cosmos.
So we've gone from a completely mysterious, invisible double flash on a random Tuesday in March through a massive international telescope scramble. We've interrogated the physics of black holes, we've dismantled the thermodynamics of neutron star bombs, and we've completely thrown out the mechanics of magnetic starquakes.
We covered a lot of ground.
We really did.
Yeah.
And we've landed on a massive physical paradox. A star-destroying explosion weighed down by its own debris, or an incredibly violent beam of relativistic light that just happened to miss Earth by a few degrees. A dirty fireball burning in the dark.
It is a truly remarkable journey from a single point of X-ray data to a profound realization about the complex, obscured, and messy nature of cosmic deaths. It serves as a reminder that every single time we look at the universe with a slightly different technological lens, whether it's X-ray, infrared, or radio, it reveals a completely new layer of physical complexity that our previous models simply hadn't anticipated.
And that leaves us with a pretty wild, slightly unsettling, lingering question to mull over. If an incredibly advanced, dedicated, state-of-the-art space telescope like the Einstein probe just barely managed to catch this faint, anomalous, dust-obscured double flash, what else is flashing in the dark right now?
It's a great question.
How many entirely new, unclassified classes of violent cosmic phenomena are playing out in the space between the stars at this exact moment, just waiting for us to invent the right kind of eyes to see them? The universe isn't just full of things we don't understand. It is absolutely overflowing with complex physical mechanics we haven't even noticed yet. And the next time you are standing outside, staring up at that quiet, dark night sky, just remember, you are completely blind to the silent, invisible violence happening right above your head.